Okay, hi everyone. Welcome to this week's C3 AI DTI seminar. My name is Manxi. I'm co-hosting this semester's seminar series with Professor Sastry and Professor Srikant, who are also at the panel today. A short introduction on C3 AI Digital Transformation Institute. C3 AI DTI supports science and technology developments that address the challenges and pressing needs in academia, industry, and society. And our weekly seminar series has the goal of featuring research that focuses on studying how artificial intelligence, machine learning, and big data can lead to scientific breakthrough with large-scale societal benefits. Here, I want to acknowledge the support from our academic partners, from the high performance computing supports, as well as the industry partners. We have a very exciting seminar series planned for this semester, the spring 2022, with a special focus on incentive design and learning for societal systems. And here is the list of the incoming speakers who will give very exciting talks. And we have had 3 wonderful speakers in the past 3 weeks. You can find the speakers' information, their talk abstracts on our website. We will also post the talk videos and slides on these websites when they become ready. Also, please subscribe to our newsletters and YouTube channel so that you don't miss our events. Okay, so today it is our great pleasure and honor to have Professor Ozdaglar from MIT here to talk about her work on optimal and differentially private data acquisition from strategic users. Professor Ozdaglar is the MathWorks Professor of Electrical Engineering and Computer Sciences at the Massachusetts Institute of Technology. She is also the department head of EECS and deputy dean of academics of the Schwarzman's College of Computing at MIT. Her research expertise broadly includes optimization theory and algorithms, game theory, machine learning, and network analysis with applications in social, economic, and financial networks. Her recent research focuses on designing incentives and algorithms for data-driven online systems with many diverse human-machine participants. Professor Ozdaglar has won many prestigious awards. She is the recipient of a Microsoft Fellowship, MIT Graduate Student Council Teaching Awards, NSF Career Award, 2008 Donald Ackman Award of the American Automatic Control Council, and many others. She is an IEEE Fellow and an invited speaker at the International Congress of Mathematicians. She served on the board of Control System Society, and she has also served as editor and area editors for many journals that include IEEE TAC and Operations Research. So Su's talk will be about 45 to 50 minutes. For the audience, please use the Q&A feature to submit your questions. We will ask them at the end of the talk to the speaker on your behalf. Without further ado, Su, the floor is yours. You can start sharing now. Yeah.
Okay, wonderful. Thank you. Thanks, Mangzi, for the kind introduction. And thanks to Srikant, Tandy, and Shankar, everyone, for inviting me here. Let me quickly share my screen. Good. I hope everyone can see this. Yep. Okay, so I will talk about a very recent paper that we completed a couple weeks ago on thinking about data acquisition from strategic and heterogeneous users. So I feel this is sort of a great venue to present this talk, because basically this talk thinks about, like optimality and different kinds of performance metrics that one can consider in these human machine online systems, and thinks about, can we actually trade off maybe accuracy, privacy losses, and that comes from these data exchanges that takes place in these societal systems. So hopefully it will be a good fit to the sort of theme of the seminar series in terms of how one can think about these questions and incentive design and learning in the context of these questions. So before I forget, this is a joint work with some brilliant people. Alireza Falla, who's a graduate student in ECS. Ali Maktoumi, who was a graduate student in ECS, but Ali is right now at Duke, a faculty member at Duke University. Azaraksh is a faculty member at Toronto. So very quickly, what's the data acquisition problem? So, of course, widespread advances in machine learning, AI, holds the huge promise to be able to offer, better services for all of us, right? Refined search results, more timely traffic data, more informative ratings, and they're therefore, basically raising the demand for user data from all of these corporations and online platforms. And some of this data is clearly available publicly, but much of it is acquired from users who do share their personal data. So this could take the form of, as a byproduct of some other transactions they're involved in, as in Netflix, or in exchange for free services they receive from, some other online platforms like Google and Facebook. But more and more, we're also seeing, explicit data markets. Nielsen is a data and market measurement firm currently offering payments to its users to collect their data. So the data transactions use and use of this data is almost certain to grow exponentially in the next 2 decades because of increasing social media applications, new mobile apps, as well as advances in integrated technologies such as IoT, and demand for data will multiply with more extensive use and applications of AI. AI is now entering into every aspect of our lives. And as I mentioned, more data markets get introduced to procure more data from individual users. So this is all great. Everybody focuses on the benefits of data. Of course, we're talking about drug discovery. We're talking about new treatments, diagnosis, and all. I talked about timely traffic data. It makes our life much better, but there's also some concerns related to these data-intensive exchanges and applications, which is privacy. So as a user's data is harnessed, more and more information about that user is uncovered and potentially utilized by these platforms and advertisers. So there's a popular solution for this tension between the benefits of data as well as its privacy costs, which is this differential privacy framework. Essentially, it limits the extent to which users' data can be utilized and uncovered by other platforms or entities. And essentially, the basic idea of DP, I will formally define this shortly, but the basic idea is it provides an upper bound on how sensitive the output of an algorithm, think about this as, for instance, a vector of recommendations on online systems, to each individual's data. So it's introduced in the seminal work of Cynthia Dwork and co-authors. It allows us to, a systematic way to quantify this sort of loss of privacy. So this actually allows us to, work with it and, being able to trade off these different considerations. It's already widely used by tech companies. But the key question, I think, that remains is, how do we really decide how much privacy an individual will obtain? I mean, if you think about it, my data may not have the same privacy value as, let's say, a politician's data. So different people have different sensitivities around how much they want their data to be protected. I mean, this is just a simple example. You have two individuals have similar data. Maybe one is more privacy conscious than the other. You want to be able to provide different privacy levels to these individuals. How do we do this? How can we elicit their privacy sensitivities? How can we design what privacy level is appropriate for these individuals? And, how do we do this overall, this incentive design problem? So this paper is an attempt to answer that question, to figure out basically how do we actually acquire data from privacy conscious users while providing guarantees on the privacy losses. We formulate this problem as follows. We consider a platform interested in estimating some underlying parameter using relevant data collected from users. So yes, we will assume users' data will be coming from some underlying distribution, and the platform's goal will be estimating the mean of this distribution. So users will benefit from the outcome of the estimation. So this is overall beneficial socially, but they're also cognizant that as they're sharing their data, privacy losses will incur. They will incur privacy losses. So this is a beautiful problem for a question for a mechanism design setting. So we will basically formulate it as users share their data in exchange for some compensation. And each user has a heterogeneous privacy sensitivity, which represents the cost per unit privacy loss. And this is his type, so it's private information. So you need to, as a platform, design a mechanism to be able to elicit this private information from these users. And individuals will participate in this mechanism by reporting their privacy sensitivity, potentially incorrectly, and sharing their data. So that's sort of the mechanism design problem we're going to formulate in this paper. But if you think about it, the mechanism involves lots of different decisions. The mechanism will design the optimal estimator. It will design what privacy level to give to each user. It will design what optimal payments it should give to these different heterogeneous users. So in order to go step by step, I will first, in the first part of the talk, I will ask the question of, suppose I have heterogeneous users and their privacy loss levels are given. So I will give Mangzi a privacy loss level of 0.4 and Shrikant a privacy loss level of 0.6. So those objects are given. And we would like to understand first, what is the optimal estimator in these in this setting? And we're going to consider two different privacy guarantees. This is common in the differential privacy framework. Two different levels of guarantees in terms of privacy losses for the users. We're going to refer to them as central and local. I will describe all that in a second. So the first part of the talk will be this setting, this more mechanistic setting where privacy loss levels are given, and we establish minimax lower bounds for the estimation error and use these lower bounds to come up with the form of the optimal estimator for central and local privacy guarantees. Once we understand the optimal estimator, we will go one step further. We'll say, okay, let me now think about this Bayesian optimal mechanism design problem, where the objective of the platform is to minimize two things, essentially the sum of the estimation error as well as the total payment it's going to make to the users. And we will show that in these two settings, central and local differential privacy, we can actually develop optimal algorithmic mechanisms to solve this problem. And the mechanism will indeed determine an optimal estimator. I'm putting optimal in quotes. I will have some caveats around that I will describe in a second. Compensation for the users as well as the privacy losses an individual will incur. So there's a growing literature on this problem of data acquisition from strategic privacy conscious users. There's several papers that uses differential privacy to quantify the cost users incur when sharing their data. I'd like to single out here a very nice seminal paper by Ghosh and Roth from 2011. So a little bit more detail about this paper is Ghosh and Roth, Selling Privacy at Auctions is the title of the paper. They assume that each user has a binary data, and they're interested, as well as heterogeneous privacy parameters, and they're interested in estimating the sum of the user's data using a differentially private and dominant strategy mechanism. So because of their focus on dominant strategy, no distributional assumptions, and because they're interested in the sum, this paper takes a worst case view, and it ends up providing a single same privacy level to all participating users, even if they have these heterogeneous sensitivities. So this thinking about when you actually do this with distributional assumptions. You know the distribution of the data, underlying data, and you're interested in some statistics of this data. That sort of was left sort of as an open question in here, and several papers, some of them in 2012 all the way to more recently, aimed at addressing this, not through Bayesian optimal mechanism design, but maybe through different ways of formulating the problem. I'd like to also single out a very nice paper by Rachel Cummings and co-authors, where they don't explicitly model privacy losses, but the idea is they consider data purchase from users that actually provide different levels of accuracy and may strategically price these different levels of accuracy for access to their data. So there's a lot of nice structural properties that you can see for mechanisms as such in that paper. So this paper, our paper, will be thinking about optimal Bayesian incentive compatible mechanisms. I think an important property is that it will lead to different privacy levels for participating users. And then we will also try to sort of contrast different architectures, sort of different market architectures, central versus local privacy guarantees, and what kind of mechanism these actually induce for the optimal setting. So that's sort of, I guess, the background. So let me now dive into describing some of these things a little more formally. So as I mentioned, we consider a platform. The platform is interested in estimating this parameter theta by collecting relevant data from a collection of users, 1 to n. And data of user I will be informative about this theta. And actually, it's a very simple model, right? So the data is just this theta, the mean, plus some noise, idiosyncratic noise. And we assume that the ZIs are IID, zero mean, with some variance var. So just remember that there's this noise that, so every agent has a noisy measurement of the underlying parameter of interest. Okay, so we will use, again, as I mentioned, differential privacy to capture the guarantees for individuals' privacy demands. So the first guarantee we're going to consider is the central differential privacy. And essentially central, think about it as it's a guarantee with respect to the impact of the individual's data on the output of the platform's estimation. And more formally, we basically consider two data sets, S and S prime. Ali Reza made this very colorful so that we all, we can all focus on it's a very nice illustration of the differential privacy. So think about two data sets that differ only in one component, ith component, and that ith component represents individual i's data. And this data sets go through an algorithm, and the output of the algorithm is A of S or A of S prime. So what central differential privacy states is that the outputs for these two data sets of that algorithm does not differ, is different by at most probability e to the epsilon I. Okay, so this is sort of something about really how much the output changes when you just change the data, one component of your data set. So I'd like to just sort of have us think a little bit about this epsilon I parameter here and what it represents. So if epsilon I is smaller, then that means from this bound that user's i's data has less impact on the output of the algorithm, implying a higher privacy guarantee or lower privacy loss. So smaller epsilon I is lower privacy loss. So you can think about epsilon I as the maximum privacy loss level that is sort of guaranteed for user I. Okay, so that's going to be our epsilon throughout the talk. So that's central differential privacy. In the central case, users trust the platform, they share their data, and they only get a privacy guarantee on the output. So they share their data, these are non-private inputs, so there's a private output. So that was you remember that was the guarantee we placed on the output of the algorithm or the estimation of this platform. In the local setting, it's a more stringent guarantee. Users do not trust the platform and they share only a private version of their input with the platform. So there's going to be private inputs, which leads to a private output. So this is more stringent. So if something is locally differentially private, it will also be private output, so meaning it will also be centrally differentially private. But I mean, definition is very similar to what I had before. We say that an algorithm is locally differentially private if it takes this private inputs, Ci of xi, and each of these Ci's satisfy this sort of guarantee that I talked about. So the guarantee here is really on the individual data points for each of the users. Okay, so that's local differential privacy, I guess this is what I just said. Local also implies central differential privacy. A canonical scheme, and this is very well known for guaranteeing these differential private guarantees, is just to add some Laplace noise to data to ensure privacy. And so what is Laplace noise? It's sort of this distribution here, exponential distribution with sort of, substantial tails. And for instance, if you have the data of users x1 to xn, linear estimator with Laplace mechanism will be in the form of linearly combine individuals' data, add Laplace noise with some parameter eta, and this is a convex combination, wi's add up to 1. Okay, and this is just something I put here, little thing, why is this estimator centrally differentially private? Well, it's actually eta wi centrally differentially private, and that you can see by exactly doing the bound that I talked about. So estimator, or the algorithm, with xi, x minus I is the same, or with xi prime. And you can compute those probabilities explicitly because of the Laplace forms, Laplace noises distribution. It's exponential, both of them are exponential. Everything is the same except this wxi and wxi prime. And because of the exponential structure, you can actually come up with an upper bound here like this. And xi and xi prime, remember, I assumed the added noise to be bound. Maybe I didn't say it. I assume for this talk that the added noise, the idiosyncratic noise on the parameter there's a support bound on its support, which is 1/2. So xi minus xi prime will be at most 1. So that guarantees immediately a differential privacy guarantee of eta wi. So that's the sort of one mechanism that ensures differential privacy. So now I think I gave the more roadmap again. Maybe this is repetition. I will first assume that these epsilon i's are given. Those are the privacy loss levels, desired privacy loss levels from the users. And we will show that linear type estimators with Laplace scheme are near optimal for both central and differential, central and local differential privacy settings. And then I will endogenize the choice of these epsilon i's by designing a proper user utility that actually captures their heterogeneous privacy sensitivities. And with those utility functions, I will embed everything into a mechanism design problem where, the mechanism outputs a differentially private estimator, privacy loss levels, and compensation as a function of what users report to you, which is their reported sensitivities. So that's the roadmap. So let me start with this part where epsilon i's are given, and let's see how we can come up with the optimal estimators. And that goes optimal, to be able to establish optimality, what we will do is we will come up with lower and upper bounds. And an upper bound, of course, will be something that's achieved by some form of estimator. And we're going to show that those match the lower bounds, establishing the optimality of the estimator we're considering. So I'll do that for both central differential privacy setting and local differentially privacy setting. And these kinds of results do exist in the literature for homogeneous privacy guarantees across users. So here, the main contribution is to consider the heterogeneity across users. And that's the whole point of our setting, because these users are heterogeneous. Okay, so what is the minimax lower bound? We assume these epsilons are given. Basically, I will define this minimax estimation error. And for that, I consider a family of distributions over my data space. I'm interested in, for a given distribution from that family, estimating the mean of this distribution. And let's assume x1 to xn are IID samples drawn from this distribution. Estimator theta hat is just a mapping from this x1 to xn and estimates exactly this mean. And then finally, QC will denote the class of epsilon centrally differential private estimators. So given all this notation and setup, the minimax error is nothing but we look at this is our estimator. This is the actual parameter we're trying to estimate. We're looking at mean square error, right? It's expectation over the data drawn from this distribution P. It's a worst case. So it's sort of maximum over all possible distributions. So worst case estimation error, and we're trying to find the best estimator. So it's the min max for that reason. Okay. So that's the object we're going to try to bound. And here is our result, which looks messy, but I'll try to get into this messiness a little bit and give some intuition of first how we get it, which I thought is very cool. And second, sort of what does it tell us about these bounds? But essentially, I don't want you to focus too much on the mathematical form here, but just that we say that there exists a lower bound with a universal constant CL, which takes this form here. So it's the maximum over some k's, 1 over n minus k plus sum of the epsilon I squares, and you get a minimum with 1, which is not super important. So that's the lower bound. The upper bound is basically saying there exists an epsilon I central differential private linear estimator that achieves this lower bound up to a logarithmic factor. So essentially this says that linear estimators in this setting will be optimal up to this log n factor. Again, as I mentioned, the difference here with respect to the literature is considering different epsilon i's. And when all the epsilon i's are the same, this basically reduces to known results in John Ducci's et al. Roth work, and it actually takes this upper bound specializes to the bound given in these works, which is 1 over n, minimum of 1 over n and 1 over n square epsilon square. So how do we get these bounds? This is the only probably a little bit technical slide I will use in this talk. It just gives a proof sketch of how to obtain these lower bounds. Basically, the key idea is to relate the lower bound problem to a hypothesis testing problem. So how do we do that? Well, so remember, we were trying to show that overall estimators min max is lower bounded. So because it's min, basically what I can show is to achieve that is for any estimator, like think about this soup and make sure there's a lower bound for that soup. So now this is soup, so I will consider a particular probability distribution, P1 and P2, two distributions, and think about gamma to be the difference between their means. Theta P1 is the mean of P1, theta P2 is the mean of P2, so it's the difference between their means. So clearly the maximum overall distributions of this thing is greater than its value for P1 and P2. Right, so this is sort of takes a convex combination between P1 and P2, and for P1, sorry, I can't see it. Yeah, so this is for P1 and P2, the exact value of this bound. Okay, so now I also do some substitution of variables. I just say instead of xi's coming from P1 and P2, I look at the estimator theta hat and I say they come from some distribution Q1, Q2. So that just is cleaning notation. So this is the thing that we're trying to lower bound, expectation of this squared distance. And I use some Markov inequality to turn it into some probability. The probability that, how much, the probability that y is different from its mean by some factor gamma. This is just some Markov type inequality. So now I'm very close to hypothesis testing. Essentially, given a realization of y, I would like to ask the question, which one of Q1 or Q2 this y comes from? So basically, I can lower bound this in terms of the probability of an incorrect output for the following algorithm, given y, choose the j for which its mean is closest to y. So I can basically ask that probability of error question in the context of hypothesis testing to be able to come up with a lower bound on this term. So why am I turning this into hypothesis testing? Because in that context, there's a beautiful method by Lecam, which lower bounds such error probabilities in terms of TV distances between Q1 and Q2, these distributions that we were talking about. So basically, I turned the problem into coming up with a lower bound on actually upper bound, because there's a minus here, on the TV distance between these two distributions, Q1 and Q2, that I arbitrarily picked with from my space. Okay, so that's the first part of the proof. The second part is basically thinking about getting this TV distance and developing a bound on this using two different ideas. So this is a distance between two distributions. And essentially, we will bound it by two terms. Some of them will come from the error because of stochasticity in the data itself. And some of it will come from differential privacy constraints that we're imposing on these distributions. So this is something, you know, we can work out. I'm not going to go into the details, but I just wanted to tell you that all these bounds involve some constraints coming from differential privacy, some constraints coming from the stochasticity of the data itself. And now I'm at a point where I can just specialize, pick two P1, P2 Bernoulli distributions, compute these bounds for those distributions, plug it back into the lower bound I was trying to get. And now I can choose. Remember, gamma was this arbitrary parameter that was the difference between the means of these distributions. I can choose gamma, optimize over gamma to get the best, tightest lower bound, and that gives me the quantity I'm looking for. Okay, perfect. So that's for the lower bound. I go into the upper bound, and I will try to show that basically the argument will be get the linear estimator in the form of, you know, I linearly combine my data plus add Laplace noise to it, and optimize over my linear estimator and show that the corresponding mean square error for this estimator matches this lower bound that I talked about. So this is not a very hard problem. So this is a linear estimator. So you look at the variance of this estimator, which is nothing but sum of the wi squares, variance of xi, which was this var, plus the Laplace noise variance is 2 over eta squared. I just minimize this over wi's, its convex values, and then I also make sure that this is differentially private, which is basically obtained by putting this upper bound here. So the interesting thing, I think I'm telling you all of these things. The interesting thing here is, which was interesting to us, it turns out that setting this to be active, you know, setting the wi's such that each of these constraints are active for all of your users leads to a suboptimal estimators. So you actually try to change sort of the privacy levels you give to different heterogeneous users, and it's not basically achieved by giving turning this constraint into an active constraint for this problem. So to see that, I think maybe I'm going too much into the details, but I like this I want to sort of convey this difference between, you know, some part of the variance coming from data stochasticity and some part coming from the noise that is because of the differential privacy. So the lower bound that we had before can be actually written as the minimum of these two quantities, 1 over n minus k star, and 1 over sum of these epsilon I squares. And it turns out that this first term is exactly this differential privacy constraint due to x1 to xk star, and this one is the data stochasticity. And for the data stochasticity, whenever data stochasticity dominates in the minimax error, what you want to do is basically, you know, these are IID samples. In order to, you know, you get from n minus k star users their data, the best estimator you can come up with is just to average them with equal weights. So whenever this is binding, you put all of the w's to be equal. And whenever differential privacy constraints are binding, then you only set them equal to the, you know, highest privacy loss you can tolerate, and basically achieve the differential privacy constraints on those users. So basically thinking about, you know, the setting k star to make sure that these two quantities are equal gives you the best upper bound or the optimal estimator that actually can match the lower bound that we have talked about. And this sort of is a figure that talks about some of these details, how you actually obtain the k star to figure out, you know, how do you construct this optimal linear estimator that can match this lower bound that I was talking about. So that is sort of in the central privacy setting. How do we come up with the optimal estimator? So you can repeat the same ideas for the local setting. The only difference is we're only optimizing over local differential private estimators. And in the case of a local differential privacy, we will show that linear estimators with Laplace mechanism are a little different from the central differential private estimators are optimal. And these basically take the form of remember we privatize all of the individual inputs for each of the users in the local case. So you do that for each of the xi's, you add Laplace noise to each one of them, you combine them linearly afterwards. And that's sort of the linear estimator that emerges in the local setting. I'm not going to go into the details. I hope I didn't lose you too much even in the first setting, but very similar arguments shows you that you can get a lower bound and show that the linear estimator that I talked about actually achieves, even without the log factor, in this case, the lower bound, establishing that such linear estimators are optimal in this sense. So, okay, and the proof is the same, as I said. It's Lecam's method, and then you construct some linear estimator, optimize over the WIs, and actually get that the optimal WI stars actually match this lower bound. Okay, so that's how we construct the optimal linear estimators. Let me now move on to the, let's see how I'm doing with time, the mechanism design part. Okay, this time I'm not going to say for each user epsilon i's are given. So I'm going to just say each user has some different privacy sensitivity or its type, the privately known type that represents his costs for privacy loss. And I'm going to assume that these CIs are coming from some distributions. Distributions are publicly known, but I only know my CIs. Other people don't know what privacy sensitivity I have. And C1 to N are the vector of my privacy sensitivities. And remember, I was considering mechanisms where individuals participate by sharing their data and reporting their privacy sensitivities. Please note here an assumption I made. The only private information is the privacy sensitivities, and data is not something that individuals can misrepresent. So this is basically the assumption that their data are either collected already by the platforms or they can be verified. So you cannot lie about your data. You can just misrepresent your privacy sensitivity. So I mean, there may be settings where this is not true, but that's not what we consider in this paper. Okay, and depending on these reported sensitivities, the platform provides a compensation to the user, and the mechanism simultaneously determines both the privacy loss levels as well as the differentially private estimator. Okay, so I will now formulate for you how we can write down this incentive design problem. Again, this is just a cartoon for exactly how this information exchange takes place. Each individual has some data xi drawn from some distribution. They have privacy sensitivities privately known. They report their privacy sensitivity, and then the mechanism outputs privacy loss levels, payments for the users, and then optimizes the estimation error. What's the user cost function? So here is how we formulate the user cost function. Each user shares their data with the platform, leading to a lower estimation error. We assume that users derive benefit from accessing this more accurate estimate. So this could be, you aggregate data from everyone and find a medical treatment that's good for everybody. Of course, this is good for everybody, but each user incurs some privacy costs because they're sharing their data. So that's the friction or trade-off that we're trying to capture here. So we model users' cost. I'm not gonna, it's more convenient to work with cost instead of utility here. Its cost from participation, we capture it by mean square error of the data as well as the privacy cost. So cost of user I with type CI, which reports some CI prime, is given by his mean square error, what he achieves out of what the overall platform achieves by from the participating users' data. So that's cost portion one. The cost portion two is loss of privacy. And I model it by, okay, he has this parameter CI, which controls how much privacy loss he incurs. And I model it linearly. So for a given privacy loss level epsilon I, CI is the per unit loss cost. So it's just a linear cost overall by having a privacy loss of epsilon I. And minus, you have some compensation. So this is, we're minimizing. So I express it as minus the payment. And okay, so mean square error is nothing but this sort of theta minus theta hat square. And if a user does not participate in the mechanism, he has no access to this more accurate estimate. He doesn't incur privacy loss and he doesn't get paid anything. So his cost in that case will be whatever his data he uses to do the estimate. Well, his best estimate given her data alone is just xi. So his cost in that case is just the variance of his measurement itself. I need that because in designing the mechanism, I need to say, but this is outside option so that, you know, I ensure a better payoff for him by participating in this mechanism. So that's the user cost function that we designed for this setup. So mechanism design problem now is very easy to state. We have a platform whose objective is to minimize the mean square error plus the payments that he's giving to each of these users. So there's some details related to, you know, generality of this mechanism, but using revelation principle, you can show that the platform can focus without loss of generality on so-called direct revelation mechanisms. And essentially that means that you can just ask the users to report their type, privacy sensitivity, and focus on mechanisms whereby reporting their type truthfully is a Bayesian-Nash equilibrium for the users, okay? This is sort of the direct revelation mechanism, and to ensure that, we impose the incentive compatibility constraints. So we want to design the mechanism such that user I has no incentive to lie or misrepresent its privacy sensitivity and this is an equilibrium concept, so we keep others actions fixed at the equilibrium, which is to report truthfully. And there's another constraint that we need to impose, which I've already alluded to, individual rationality or participation constraints. The platform, through this mechanism, does not make users worse off by participating in the mechanism. So a platform's problem here is basically minimize this cost subject to incentive compatibility constraints for each users, as well as the IR constraints. Once you formulate the problem like this, so now next part is the solution. And for those who know Meyerson's seminal work of designing optimal auctions or single-dimensional mechanism design, you will see that our analysis has a lot of similarities to that, with the exception of the user cost having a different form. But basically, the steps will follow similar structure. We will basically first, look at sort of these interim quantities, like the payment as a function of my own type, and privacy loss level as a function of my own type. And the first result characterizes the payments for both central and local privacy data acquisition mechanisms that can satisfy incentive compatibility and individual rationality constraints, if and only if this expression holds. So what this is saying is, if you want any payment, which is remember, this was our optimization problem, we're choosing the payments, right? If you're looking at the optimal, no, actually not optimal, any payments that satisfy IC and IR constraints need to take this form. And that basically you can prove by just looking at, IC constraints is really a maximization constraint for each user. So you look at that maximization problem, you look at its first order conditions of these IC constraints, and then you plug into IR constraint to show that, there's such a relation between the variables of your problem, epsilons and payments and so on. And there's a constant here that you need to pin down. And if you're thinking about optimal mechanisms, meaning you want to minimize total payment, you set DI equal to 0. So that's the first key lemma for characterizing the optimal mechanism. Then basically, if I have this payment form, if I know that anything that satisfies IC and IR has that expression, I just, plug in that payment form here. Now I know any payment which has that form satisfy IC and IR, so I can forget about IC and IR. One thing I forgot though, another thing it's important to impose on the problem is to make sure these epsilon i's, which are also the optimization variables, are decreasing in Z. So essentially what I can do is plug in T's to my optimal mechanism design problem. I drop IC and IR constraints now. They're already embedded in the structure of my payments. And I reduce the problem into just a minimization problem for a particular estimator. It's a minimization problem over privacy loss levels now of this cost function where TI structure is embedded. And I also need to make sure this epsilon I is decreasing because that was a condition in the characterization of the payments that I've outlined. Okay, so that makes the problem. I'm slowly going to go from an infinite dimensional optimization problem to a more simpler problem that I can say something about for its explicit characterization. And another thing I forgot to say is in writing these things, there's this new function that popped out. This is sort of the virtual cost, similar to Meyerson, but it's different than Meyerson's representation. And in order to do this optimal characterization, this is standard in mechanism design literature. I will assume that this virtual cost is increasing in C. And it holds for a variety. This is just a transformation on the distribution on this privacy sensitivities. And many distributions, such as uniform, any log concave density, uniform exponential normal, satisfy this increasing assumption. So it's not a super restrictive assumption. Okay, so I will just show you now. From now on, I will do a trick. And this is something that's sort of a little bit open question in this work. I will focus on linear estimators and characterize my optimal mechanism from this point onward for these linear estimators. So my argument is that we have shown linear estimators to be optimal for given epsilons. Of course, that doesn't say that linear estimators will be optimal for my problem as well, because I'm designing these epsilons, but it gives me hope at least that they're a good benchmark to start from. So it's an open question to think about the optimal estimators even in this problem itself. But having said that, let me focus on linear estimators. For those linear estimators, I can write down the mean square error explicitly. And then, when I plug it in back in my mechanism design problem, I now turn the problem into really finite dimensional problem where I'm just choosing this epsilons, weights, and the eta, differential privacy level, noise that I'm adding, right? I'm adding this Laplace noise with parameter eta, and I have to design this eta as well to be able to guarantee the epsilon I levels for each of these users. So that's now my problem, okay? Okay, one thing is here there's this constraint on that relates my optimization variables, W's and epsilons. Because this problem is increasing in epsilon, one can show that this constraint has to be active for all I. And once you substitute W, when they're active, you can substitute for Wi as epsilon I over eta. You get this problem. This is now your mechanism design problem. It's an optimization problem, not an easy one, but at least much more friendly looking than the initial mechanism design problem that I started from. And you can show that also the optimal solution here. Remember, I had a constraint to achieve true optimality, that this epsilon i's have to be increasing. And it turns out that you can show because of our assumption on the virtual costs, that ensures that the optimal solution here satisfies that. And therefore, this is exactly the solution of this much simpler problem is exactly my optimal mechanism for the problem I started from. So this is all good, except this is not an easy problem to solve either. This is a problem in epsilons. You have these weird dependencies. It's not a convex problem. So what we do is basically, even though it's a hard problem, one can actually do some tricks to show that it actually has can be solved exactly in polynomial time, which is n log n. Okay, and let me see if I'm running out of time. I have a few minutes maybe to tell you how we can achieve that. So for given CIs, I first sort these virtual costs. That takes n log n time. And then the difficulty in this problem is this denominator here, right? If I did not have that, it would be a nice convex problem. So what I do is to kill that denominator, I do some change of variables. I call this thing to be some S. S is sum of the epsilon i's. And with that S, now I introduce more variables. I didn't do anything fancy, but basically I turned this into a problem in S and epsilon i's together. So for a given S now, my problem became a convex problem. And okay, so then for a given S, I can solve this problem because it's convex. I look at the optimality conditions. It gives me epsilon i's to have this form as a function of the S and lambda. Lambda here is the Lagrange multiplier for this particular constraint. So what I can do is I can go plug it back in the problem instead of the epsilons. I will have now a problem in terms of S and lambda, right? And so now let me go back to why I was sorting these things. If I actually now know that lambda is between psi1 and psi2, I can actually pin down these pluses. It will be either 0 or some linear term in here. And with that assumption, I can solve this problem in closed form because magically it turns out to be root of a degree 4 polynomial. So for each such lambda in these intervals, I can come up with the closed form solution. So if I do this for all possible intervals, which is n of them, then, well, solution, closed form solution is O of 1. I have n of them, which is O of n. Together with my sorting, which is n log n, that gives me basically the exact solution in time of n log n. So that's sort of the structure of this algorithmic optimal mechanism for solving this problem. Okay, good. Maybe I actually, I do the similar, very similar tricks for local differential privacy. I, turn the problem into a simpler problem. It's a non-convex problem again. This turns out to be a little bit harder, so we don't have exact solution. But what we were able to show is that in polynomial time, again, you can come up with an epsilon approximate solution for this problem. And let me not go over the details because it's really very, very similar. So you use KKT conditions, you convexify some parts of the problem, and then you try to use the structure of the problem as much as possible to be able to come up with an approximate solution that can be obtained efficiently. Okay, so I want to spend maybe just a few minutes, remaining minutes, in terms of how do these mechanisms, optimal mechanisms that we've designed now, look like for central versus local differential privacy guarantees. So the first thing is the natural question to ask is, so there are the two privacy guarantees I can enable. How does the platform's objective function change for a central versus local differential privacy guarantee that I can, provide to the users? So, to answer that question, we need to understand some implications between, local and central differential. So, because remember, we were designing this mechanism over all estimators that are local or central differentially private. So remember, I mentioned before that local differential privacy is a more stringent requirement. So any locally differential private estimator is centrally differentially private. That means that local estimators is a smaller set compared to central DP estimators. And if I'm minimizing over these sets, because central one is a bigger set, of course, the minimum value will be smaller. So platform's optimal objective will be smaller or better with central differential privacy. So there's some caveats to this because we're focusing on linear estimators. So linear local estimator is not necessarily linear central estimator, but without going into the details, because I think I'm saying too many things, I don't want to confuse you, but essentially you can do some more arguments along what I just described here to show that with central differential privacy, the platform objective in terms of getting a better accuracy, as well as, the payments it provides to the users is always smaller. So platform is better off with a central guarantee compared to local, which also makes, I guess, sense because local is a stricter guarantee for the users. So to be able to do that, platform pays more in terms of accuracy as well as the payments. This is just a simple example to illustrate exactly what I said. We plotted for a simple two-user case platform's objective function as a function of C1 and C2 for the central setting, local setting, and local minus central. And remember, I said local is always, central is always lower than local. So local minus central is always positive. And that's exactly, if you look at the color code here, it's always positive. And another interesting thing to note is the two actually, the objectives that are obtained under local and central is 0 when C1 and C2 are very different from each other. And that's the intuition there is when C1 and C2 are very different from each other, you have one user which is extremely privacy conscious and one is not. And you basically then, in that case, obtain all of your data from one of the users. And therefore, central and local differential privacy guarantees there coincide. So optimal objectives are exactly the same. The next sort of setting is an illustrative example for, okay, you have these two mechanisms. One is guaranteeing central privacy losses. The other one is local privacy losses. How do these loss levels provided at the optimal mechanisms compare? This was something a little, surprising for us because we thought, because local is a more stringent guarantee, we thought that the loss levels you can guarantee in the local setting will be higher. And this example shows that that's not necessarily the case. So there's a formal, this was an example. So we also say, we provide it a little bit more generally than that particular example and say that it's not clear. That's all I want to say. So because of the payments and then all these strategic considerations, because of the structure of central and local differential private estimators, it turns out that in the optimal mechanism, the privacy loss levels guaranteed for users may be higher or lower in the central and the local cases. So I guess I am almost out of time. So I would like to leave a few minutes for the questions. So this is, I hope I was able to give you the gist of the main results and the objectives here. It's really about designing incentives to be able to trade off, accuracy, privacy, compensations when you have these heterogeneous users and when data is decentralized across these users. I think the most important aspect of this paper is this heterogeneous users. We essentially constructed optimal estimators for heterogeneous users and then plugged all of that into this sort of incentive design problem under different market architectures. I feel like this is just, scratching the surface of these very broad set of questions. It motivates a lot of questions about how you design incentives for optimal data acquisition, trading off multiple performance metrics. So you can have different learning objectives. You don't need to just learn the mean. You can think about regression problems. You can think about other learning problems. You can think about more nuanced notions of privacy. So the privacy guarantees or privacy notion I talked about is only about individual privacy here. I think another very interesting question is to think about, the fact that the data has some social value. So when you're giving data about yourself, you're also revealing, characteristics for users that have the same demographics as you do. So that's another very interesting, I think, dimension of all these problems, social nature of data. How do we think about differential privacy when you incorporate the social nature and many other performance metrics that one can think about? So with that, maybe let me conclude, Mangsi, and see if I can have any questions.
Thank you, Asu, for the terrific talk. And thanks, everyone. So we're open the Q&A for both the audience and the panelists. So yeah, for the panelists, if you have questions, please unmute yourself.
Maybe I'll start off with a question. That was a great
yes, good. These are things we looked at together. So I was like hoping a question from you. Awesome.
So I guess if I understood it correctly, the setting is some sort of a linear setting, like mean estimation, right? You're trying, you have a bunch of random, you have some data and then you add noise to it. I guess you've worked on yourself on trying to learn some parameter data of some distribution, for example. I mean, could that, so would these results extend to that kind of a setting? where basically you're getting information, but you're trying to learn something about the population through some parameter that is used to generate this each of the individual random variables. So or is it very, very specific to this linear theta plus wi setting? Yeah.
Yeah, so I think the linear, depending on what parameters you want to learn, right? Sort of thinking about if it's not mean, if it's some other statistics.
Yeah, higher moments, let's say.
Higher order moments could be. I think one can still use linear estimators. Optimality I need to think about. But I mean, if you remember in the second part of the talk, we just said, for linear estimators, how do you design this mechanism design? So the second part is a little bit separate from the first part. So I think for the first part, we can think about other parameters. In the first part, there's nothing strategic. So it's not social learning. I just get data. It's basically just a differentially private estimation. And what are the optimal estimators in that setting? Changes depending on the statistics or changes depending on the problem we're developing. So even in this setting, in the simplest setting, I mentioned it in the talk, it's, the mechanism design problem also asks the question of what's the optimal estimator. It's not clear when you think about payments and all these other considerations that the linear estimator is the optimal thing in that setting. And I think that's a very interesting question I would love to tackle. What is the optimal estimator? But one can think about, within the class of linear estimators, how do we design the optimal ones? But is that clear? Like, I think there's a difference between,
Yeah. So what I meant by linear was I meant the theta plus adding noise. That's what I meant. I mean, I was thinking, what about higher moments or some other parameter of the distribution? And would that change the setting completely, or would it change the results completely, or whether it is? So I was thinking that the xi that you have is comes from some distribution, and and trying to learn the parameter of the distribution, and whether that would change the results, or whether, at least qualitatively, it seems like it should be similar, but
it's very similar. I think I want to say linear estimator will still be optimal as long as it's but I think I need to think about it a little more carefully to make sure. I know you just want to say a parameter of the distribution. It's not additive linearly. What happens? Yeah.
Yeah. Okay.
I think it is still optimal, but we may need to have some conditions.
So I have another question, which is a philosophical question.
Shrikant, can I get in one before?
Okay, go ahead.
Fantastic set of techniques. We are teaching a class, so I think we're going to try to feature some of Manshi's teaching actually during the teaching. A fantastic set of techniques. Let me ask you, so by the way, it's also one of the times that I've seen some wonderful results on differential privacy. But have you thought about applying these techniques to what is sometimes referred to as utility-based privacy, which means that people give up information in the expectation of receiving a reward, right? So that's a model for when you part with private information. And so it seems to me, what I was excited about your talk is, I'm sure the methods, there was an Illinois guy, I don't think he's on the call, on the listening, Roy Dong, who started doing this, and he actually engaged with Cynthia on trying to do an rapprochement between the two. But what I got excited from listening to you is that maybe you have all the techniques to. Yep. So
you beautiful question, Shankar. Really, I just try to highlight different components. DP is just one component in allowing us to guarantee to formalize the privacy guarantee that users demand. It's not the only approach. We could put a utility-based
for other frameworks.
It's absolutely another paper we should do. So you can actually write down the utility function in a way that captures, this. It's just another cost function. If you actually want to design it as a reward cost for the privacy, that's something we can add. I think the linearity of the estimator, going back to Shrikant's question, has enabled us to solve the mechanism design problem explicitly. You know, it's not an explicit solution, but you know, you get the exact solution algorithmically. So the linearity was helpful. Linear estimator was helpful in enabling that. But as long as I think one can think about different forms, maybe we don't get it fully exactly, but maybe approximate it. I think different components can be generalized here. There's many assumptions I made, you know, like I assumed privacy sensitivity is independent of the data. I assume data cannot be misrepresented. All of those things I think we can work on, you know, expanding from the starting point.
Very good. Fantastic. Great talk. And I love you know, I was just telling everybody in the room around me, the cleverness of your proofs always really wonderful to watch.
That's Ali Reza's proof. That's correct.
Wow.
Yeah.
Hats off. Okay. And now I think Shrikant asked the rest of his question, and I think the others all might also.
If there's no other question, I want to understand sort of the difference between local and, did you call it global privacy? I mean, I understand the difference mathematically central. I understand it mathematically, but I was just trying to figure out what, from a user's perspective, is it easier to provide local privacy constraints or central privacy? I don't know how as a user, I would think of central privacy. I mean, it's more of a philosophical question. It's not a technical question.
It is actually a very good question. I mean, I'm just learning this myself as well, but basically central is you send, you know, it's a guarantee when you trust the platform. You send your data to the platform, and you have a guarantee in terms of how your data impacts just the output of the platform. That just the output of this, you know, estimation process of the platform. So the trust in that case, that you need to have a trustworthy platform to be able to guarantee that notion of privacy. If you don't, you cannot. So you need to go back to local.
I see. Okay. That's the way to think about it. So if there's a platform that you trust, then this might make sense. But otherwise,
this is achievable. Think about this as achievable in that case only.
Okay.
Yeah. Thanks. So I also want to ask about this difference between central and local. Like, from the mechanism design formulation in this work, if the so central versus local affects both the monetary incentive that data providers receive, as well as the algorithmically what is the MSE, the estimator, right? So if combining these two things together and the agents are able to choose between central versus local, which one are they going to prefer? Like in terms of the total utility they can get, combining the estimating quality as well as the payment they get.
So that's what I was trying to do at the end, right? So I actually looked at platform and then say, you know, the optimal mechanism for central actually gives the platform a better objective.
Right, but for the player, the agent's perspective.
Okay. For the agents, we looked at the privacy loss levels that they get under these two architectures, and it's not clear.
Okay, I see.
Okay. That way. Yeah. So there may be other things to look at, Mengzi. We haven't looked at everything, but it's a very good question because there's so many. This is different than Meyerson, right? Meyerson only is about
it's a comparing the outcome between two mechanisms.
You know, they care. I think an important modeling feature here of this paper, which I haven't seen in other papers, is users care about the overall accuracy, estimation.
Yes.
So there's an alignment with the social objective. There's the local loss, and there's the payments. So that makes it pretty strange in terms of how these things work out. Right. Yeah.
Thank you. That explains.
A great question as usual.
Thank you. Are there any questions from the audience or the panelists? Okay. If not, let's thank so again for the terrific talk and
thank you. Great to see you all. Thank you.
Good to see you.
Talk to you more. Thank you. Bye.
Thank you. Bye-bye.